Okay, we're finally into how to make a full confidence interval today for a population proportion. So this is a one proportion confidence interval. We're going to learn lots of different versions of this. This is the homework this spring, but this is the start. It's very exciting. Okay, so conditions. So one of the things that's nice is what we've been doing the last chapter kind of prepares you for this. It's very similar. So the three conditions are two of them you've already done. So with proportions, we already know before you do standard deviation, you should check the 10% condition. Before you do a normal curve, you should check the large counts condition. This is a new one. You want to take the data comes from a random sample. And that's pretty normal with all of the different confidence intervals we're going to do. We always need some randomness, in this case a random sample. If it was an experiment, we would need random assignment, but usually it's going to be a random sample for these. Typically, we don't do a ton of experiments with this. Okay, so Mr. Buckley's class wants to construct a confidence interval for P. P is the proportion of red beads in the container, which contains 3,000 beads. The class's random sample of 251 beads had 107 red beads and 144 were some other color. Check whether the conditions for constructing a confidence interval for P are met. So let's just look at the conditions first. Was this a random sample? Check. We got that. It says the class has random sample, so you would say random sample, check, or something like that. And then the second one, less than 10% condition. So 251 was the sample size, N. Is that less than 10% of 3,000? It is. So 251 is less than 10% of 3,000. That's true. So we check the second condition. Third one is N, P, and N1 minus P have to be greater than or equal to 10. In this case, they gave us the two numbers there, essentially the successes and fails. 107 were the NP, and 144 was the N1 minus P. So you could calculate those by multiplying N times 251 times the proportion there, or you just say, hey, I already know it's 107 and 144. Those numbers are both bigger than 10. So again, you could calculate it, or you could just kind of know, oh, they gave me the successes and fails there. So it kind of depends how you want to do it there. The margin of error of an estimate describes how far at most we expect the point estimate to vary from the population parameter. We'll talk more about margin of error. It's kind of like a plus or minus. Like with political polls, it's always 3%, but for other things, it's going to be different. The critical value is a weird thing. Critical value is called, so when you see that critical value, we're going to use this notation. So the critical value is Z critical value. So that when you see that Z with a star there in the exponent spot, that means the critical value. Critical value is a multiplier that makes the interval wide enough to have the stated capture rate. Okay, so we'll learn how to calculate the critical value and so forth. The generic formula for confidence interval is included on the formula sheet. That's nice. That is the generic formula. So statistic plus or minus the critical value, Z critical value, times the standard error of the statistic. Okay. So this is the formula for standard error. I believe this is on your formula sheet as well. This is for proportions. So it's pretty much, standard error is basically the same formula as standard deviation for proportions. It's slightly different because we're using P hat and not P. We don't know the true population proportion. We just took a sample. So because it's a sample and not actually P times 1 minus P over N, but it's P hat, because it's just from a sample, we call it the standard error, but it's essentially, it's kind of like the standard deviation of the P hat there, so of the proportion, but it's called standard error, very similar to standard deviation, works about the same. Yeah, they give you the generic formula, and then they do give you the standard error formula. But you kind of put it together to get this formula right here, so to speak. So you put p hat is in the middle, plus or minus z critical value times the standard error. So kind of putting those two ideas together, you get this formula there. Those two on the left are on your formula sheet. That is not technically on your formula sheet, but you can kind of piece it together with what they gave you, especially once you get used to this. Z critical value is the value for the standard normal curve with C percentage area between that. So the percentage confidence level will tell us how to get Z basically. Okay, so according to a 2022 Pew Research Center report, 75% of U.S. adults have read a book in the previous 12 months. That's nice. This estimate was based on a random sample of 1,502 adults. Determine the Z critical value for a 99% confidence interval for a population proportion. So the way you do that is you kind of have to, so this is how I do it. So for Z critical value for the 99%, so you draw kind of a generic normal curve, and in the middle you put 99%, which means kind of by default, there's a 0.5% or 0.5%, 0.5% on each side here. There's 0.5% on each side. We essentially want to get this value, this Z critical value, right? Is the Z value for that spot on the graph. So essentially we're kind of shading to the left of this. So all this area is shaded. Well, I only have 0.5% to the right. So we're actually shading 99.5% to the left of that point. So you're going to use inverse norm. And you're going to put the 0.995 because that's 99.5%. So let's go to your calculator. See if we can do this. So go to calculator page, menu. Let's see. So we need inverse. Maybe 653, I believe, is inverse normal, and 0.995. You can just leave the default like it is for z-scores 0 and 1. And the z-score there is 2.58, I guess, if you're going to round up, 2.58. So 2.58, see what they came up with. They do a similar one. They found the negative one. I prefer to find the positive one there because you always want to use the positive value. If you find the negative value and just put in 0.005 for the area when you do inverse norm, I get to make sure that z-score is positive. So you just have to make it positive. So I always find the one on the right because it comes out positive, but what you want the Z critical value to be positive. There is a way to use a table, but we don't use that. It's going to be easier to use our calculator. According to, again, the same problem, calculate the standard error. So we need the formula, right? So the formula was, if I remember right, let me see. So it was p hat plus or minus Z critical value times square root of p hat times 1 minus p hat over n. Okay, so p hat was 75, so 0.75 plus or minus 2.58, I think was our Z critical value, times the square root of 0.75 times 0.25 over n, which is 1502. That's all, it's hard to see, but that's all underneath the square root. So it's one big square root of that fraction. So it's not a square root in the numerator, it's the whole fraction is being square rooted. Type that guy in your calculator, and you should get, yeah, I did it right. Okay, so you should get 0.11 for that. So if you put it all together, you get 0.75 plus 2.58 times all that, which was 0.011. And so to just show you how to do this in a calculator in case you're struggling. So what I would do is I would type in 0.75 plus 2.58 times square root of the fraction control divide 0.75 times 0.25 over, I think, 1502. That gives you the positive case, and then if you copy and paste and change that to minus, it'll give you it gives you the lower bound and upper bound there. So the lower bound would be 0.7211, and the upper bound is 0.7788. Doing that, so they get those two. They like to write it almost looks like an ordered pair, but that's kind of like interval notation: lower bound, comma, upper bound. And that is our interval. So our interval, our one proportion. That's what we've been trying to do: is create a one proportion z interval there. So it's from 0.722 or 72.2% to 77.8%. So that's how you do it. That's how you create an interval. Let me show you how to do the do part in your calculator there, because it is actually possible. So let's try this, see if this works. It's been a while, so let's see if I can do this. So let's see, we want confidence intervals. I'm pretty sure it's that one. And then we want one prop z interval. I think that's what this is called. So let's see. So success rate. So x is the number of successes we want. But we have to find the number of successes. So let's do that. So let's find, 0.75 times 1502. We want a total of 1,127 successes. So let's go back to that menu 6. What was that number? 1127. Confidence intervals. I think it's 1127. I rounded to the nearest whole number. I think n has to be a whole number. I could be wrong on that. 1502. So that's 75% of 1502 there. And the confidence level was 99, so 0.99, I think is what they said. So then you just say okay, and oh my goodness, so it creates, 0.722, 0.779. Yeah, so you get slightly different answers. Now I want to try this, so I just want to see, because I don't remember. So 6.5. If I put in the exact number, it gives me an error. So I thought that might happen. You do have to put in a whole number, so that's why I rounded that one. That was from memory, and it worked. So it gives you p hat is 0.75033. That's slightly off because, again, our value there we had to round. Our margin of error. So margin of error is really the z critical value times the standard error there. So it does give you that. And it gives you n. And the lower and upper is the most important part. And we understand as stat readers that if you come up with this number, it's 0.779 instead of 0.778. These are, this is because you used the calculator one, maybe didn't round or did round. We understand that as long as you show your work is showing the command when you do this. So let's see what they would expect here. I think they'll probably do this in a minute. No, they didn't say anything about that. I thought they would say, so you would say, one prop z interval, label the values. Let's see, I think they will say this probably in a minute. No, they didn't. They didn't mention it. So, you want to put the values you entered there to get that. So when you go to one prop z interval, let's go to it. Menu 6, 6, 5. So number of successes, x, the n value, and then the confidence level is what you put in there. If you were in class today, you might have gotten this form. So this is just a page with some of the instructions on what to do. It kind of walks you through a full problem. So we're going to do this full problem here. So a recent poll of 738 randomly selected cell phone users found that 170 of the respondents admitted to walking into something or someone while talking on their cell phone. Constructed 95% confidence interval for the proportion of cell phone users who admit to walking into something or someone while walking on their cell phone. So it's a 4-step process. So first, state, so that's the top of this. So it says, state the parameter and the confidence level. So it's a 95% confidence level. P is the proportion of all cell phone users who admit to walking into something. So just talk about the context of the problem. It's a proportion, not a mean here, so that's a key word to use when you're defining that proportion, the parameter there. So we like to call the name of the method, this is a one prop Z interval. One sample Z interval, one prop Z interval, those are both fine to say. What are the three conditions? Random, was this from a random sample? It does randomly select a cell phone user, so a random sample. We like to use the word sample there, even though they didn't use that means random sample there. Less than 10% conditions, so 170 is less, let's see. It's reasonable to say that 738 is less than 10% of all cell phone users. That's certainly reasonable. And then the NP, so that would be, well, we know 170 is the number of successes, and then 738 minus 170 is the number of failures. So that's how I would get it. You could do n times p hat there if you wanted to get that, and n times 1 minus p hat. But 170 and 578 are both at least 10, so it passes that condition for the normal condition. Constructed 95% confidence interval, so again, we just did that. That's just rehashing that. They're showing how you could use NP hat there if you wanted to, but you're going to get the same answer. If all the conditions are met, we can perform the calculations. So start with P hat, right, it's 0.230. In this case, if we use our calculator, 170 is nice because it's already done for us. The formula is P hat, so P hat is 0.230 plus, now we have to do for 95%, so let's do that. So for 95%, let's do the Z critical value. So I like to draw a generic one with 0.95. So that's 5% left over, so that means 2.5% is left over right there. So if you do inverse norm, 97.5% of the data, and you do the defaults there for that, is going to be there. So to find the Z critical value, you go menu 653 and then 0.975. So 1.96. So that's a very popular number. You might end up memorizing the number 1.96 because it's so popular, because 95 percentile is the most common one we'll use. So now we have the Z critical value. You would need to do the square root to find the critical or the standard error, square root of the fraction 0.230 times 0.1 minus that, 0.77, I believe, over n, which was, I believe, 738. And you get that value. So again, they got all those values, they put them together into that formula, and they're going to use their calculator at that point to type it in first time with a plus, copy and paste it, type it in with a minus. They simplified the margin of error there, which is fine to do, and then they added and subtracted, and they get 0.2. Let's do this with our calculator and see if we get the same answer. So menu 665, I believe, is one prop Z interval. So n is the number of successes. I think that was 170 out of 738. With a 95, it defaults to 95 because it's so common. And we get the lower bound of 1.999, which is 0.2, and 0.2607, which is 0.260. And so those are the values we get when we do that. Using technology, we got slightly different numbers, and that's okay. Interpret your interval in context. So that's the last step. Remember, we did that a lot, the last section. which is nice. We are 95% confident the interval from blank to blank, 0.2 to 0.261, captures the true proportion of all cell phone users who admit to walking into something while talking on their cell phone. Interpret the 95% confidence level. So if we created many, all possible samples of size 738 from the same population, we created many confidence intervals. About 95% of the confidence intervals would contain the true proportion of blah, blah, blah. They said it's slightly different, but that's the idea of it. So interesting on the do step, so all that calculations. If you opt for the calculator only method, be sure to complete 3 other steps and give the interval in the do step like that. So give it in that order. Okay. A Pew Research poll interviewed a random sample of almost 12,000 adults about their views on sports. Of those surveyed, 62% said they follow professional college sports not too closely or not at all closely. 21% they follow sports somewhat closely, and 16% they follow them extremely or very closely. Let P of the people is a proportion of all these adults who follow sports extremely or very closely. Check whether the conditions for constructing a confidence interval for P are met. So just check the conditions. So random, is this random sample? It says that in the first sentence, so random sample, check. Random sample of almost 12,000 adults. Less than 10%. So it was 12,000 adults from 12,000 or 11,945 is less than 10% of all US adults. That's true. And then finally, the large count condition. So N times P. So 11,945 times, that's interesting. So P is extremely or very closely. So 16%. So the almost 12,000 number times 0.16 is bigger than 10, and the almost 12,000 number times 1 minus 0.16 is that one. Yeah, so 0.84 there. So they just said both those are greater or equal to 10 there. Good. A large high school with 1,853 students is opening a student-run coffee shop called the Breakfast Bistro. The bistro plans to offer hot coffee and breakfast items, so it needs to estimate the percentage of students who will patronize the shop. A random sample of 120 students is surveyed, and 33 students said they would patronize the bistro. Determine the critical value Z for a 90% confidence interval for a population proportion. So again, you want to kind of, go 90%, so 0.9, which means there's 10% total on those two. So that means there's 5% over here. So you're going to do inverse norm 0.95 because, again, 95% is to the left of that line right there, which is what you're trying to get. Calculate the standard error. So that would be standard error. The formula is square root of P, which is 33 out of 120, whatever that fraction is, times 1 minus P. So that fraction would be, I think it's 87, if I did that right, over 120, 1 minus 33, or 120 minus 33. I think that's right. And then over N, which is random sample of 120, so 120, and you'll get that number. And then construct a 90% confidence interval. So again, you're going to take the P hat plus or minus the Z critical value, which you got from the previous problem, times whatever this number is that goes there. So they showed the work here. They got 1.645, so 1.65 for the Z critical value for part A. They did P hat was 0.275, so standard error is 0.041. and then they put all that together to get 0.208. We could also do this in our calculator just to make sure that everything looks correct there. So if we did that, it would be menu 665. So N is the number of successes. I think there were 33 students successful out of 120. And it was a 0.9, I believe, was the confidence level. Should get 0.2079, 0.208, and 0.342. That looks right. Good. To become a U.S. citizen, prospective candidates must pass a test on U.S. government and history. To pass the test, an individual must correctly answer 60% or more of the questions. 3 student researchers wanted to estimate the proportion of their school's 1,853 students who would pass the test with 98% confidence. Of the 104 students they randomly selected to take the test, 71.1% scored well enough to pass. Interpret the confidence level. So this was 98% confidence level. So if we took many samples of size 1853 from the same population, we created many confidence intervals, about 98% of the confidence intervals would contain the true proportion of, and then talk about this problem in context. See what they did. We captured the true proportion of all 1,853 students at their school who passed the test. Oh, by the way, I said that wrong. So random samples, every possible combination of 104 students. So the sample N was 104, 1853 was the total population there. Construct and interpret a 98% confidence interval for the proportion of all students, of all 1853 students of the school that passed the test. Just do some calculations there. So the 98%, so that would be 0.98. So there's 1% over here, 1% over here. So that would be inverse norm 0.99, and then default to get your Z critical value, and so forth. And so if you calculate that, and again, you put 0.711 for your p hat there. So we're using the p hat and the 1 minus p hat in the standard error formula, which is very similar to that standard deviation formula. And just to check that we did it right, I love that you can do it this way, right? So menu 665. So N was 104, I believe, out of 1853. And the confidence level is 0.98. Should be 0.043. Wait, what did I do wrong? 74 out of 104. Yeah, that would be the difference. Menu 665. So 74 was the number of successes. That was from our large counts condition. That's one advantage of doing the large counts is it helps keep you honest as this one. So out of a total of 104, confidence level was 0.98, I believe. Yeah, I think that looks about right. Yes. Yeah, so the large counts really helps you figure out what your number of successes and fails are if it's not listed easily in the problem, like this one wasn't. They didn't really list out 74. By the way, that's a rounded number. You can tell because it says approximately 74. If we actually did 104 times 0.711, we get that. So we want to round that because the number of successes has to be an integer there. So that's important. That's your lesson for today.